We're going to close out this unit with a discussion of something called cardinality. So suppose you have two sets A and B. If there is a bijection between them, we say that the two sets have the same cardinality. Sometimes two sets might be able to construct a bijection between them, and sometimes you might not. If you can, if such a bijection exists, you say they have the same cardinality, and you write it as follows, and you say this as the cardinality of A equals the cardinality of B. Cardinality is a way to talk about how big sets are. That's why we have the same notation as absolute value. It's basically saying the size of A is the same as the size of B. How do I measure size of sets? Whether or not bijections exist between them. So for example, the set ABC and the set 1, 2, 3 have the same cardinality. How do I know these two sets have the same cardinality? Because I can construct a function from one set to the other as follows. F of A is 1, F of B is 2, F of C is 3. It's a bijection. Okay, it's injective. I never got out the same thing more than once. It's surjective. I got out everything I could have hoped for. So this is a bijection. Since a bijection was able to be constructed between these two sets, they have the same cardinality. This is not the only bijection between the two sets. Okay, there are actually 6 of them, but this is a bijection between them, so there is one to be found. They have the same cardinality. For small sets, this is fine. If I give you 2 small sets and ask you to construct a bijection between them, you can generally just sort of do it. But intuition can be a bit misleading when the sets get really big. For example, the natural numbers and the integers have the same cardinality. This might strike you as a bit weird because the natural numbers are a subset of the integers, and it's not all of them. Okay, these are not the same set, but this set of natural numbers is a subset of the integers. But I'm claiming you can actually establish a bijection between them. Here's a function that works, and again, it's not the only one. If you have an even natural number, spit out n over 2. If you have an odd natural number, compute n plus 1, then divide by 2, and take -1 times that. This is actually a bijection whose domain is the natural numbers and whose range is all integers, meaning there's a bijection between the natural numbers and the integers. They have the same cardinality. There are exactly as many natural numbers as there are integers, even though the natural numbers are a subset of the integers. Okay, so we're not going to go through the proof of this. You should be able to prove this function is bijective, namely injective and surjective. Cardinality defines an equivalence relation in quotes. Okay, we can't talk about the set of all sets. Okay, we discussed that back in our discussion of Russell's paradox. However, bijections give us some useful observations. The identity function is always a bijection, so a set is always the same cardinality as itself, because the identity function does provide a bijection from a set to itself. Bijections have inverses which are bijections. So if I can make a bijection from A to B, its inverse gives a bijection from B to A. So if A has the same cardinality as B, then B has the same cardinality as A. In other words, cardinality is somehow symmetric. And the composition of 2 bijections is a bijection. So if I can make a bijection from A to B and then one from B to C, I can compose them and get a bijection from A to C. In other words, if A has the same cardinality as B and B has the same cardinality as C, then A has the same cardinality as C. So the property of having the same cardinality is also transitive. So we have reflexive, symmetric, and transitive properties of relations here. Every set has the same cardinality as itself. If A has the same cardinality as B, then B has the same cardinality of A. If A is the same as B and B is the same as C, then A is the same as C. But I'm not really going to call this a relation between sets, because I don't want to somehow talk about the set of all sets. And relations were defined as subsets of product sets, and I don't want to start taking the product set of the set of all sets with itself. So we're being a little informal here. Okay. So this is something like cardinality, and we can define something like equivalence classes. All sets that have the same cardinality can kind of be grouped together in a equivalence class with air quotes around it, into a single object representing all the sets that have the same cardinality. Now, this isn't technically a set. As we've said, Russell's paradox really prohibits making things like the set of all sets. but it is something. It's a collection of all sets that have the same cardinality. But they're not actually sets. Okay, now there's something called the Schroder-Bernstein theorem. It says the following. If A and B are two sets, and I can construct an injection from A to B and a surjection from A to B. So by being clever in one way, I can make an injection from A to B. But by being clever a different way, I can make a surjection from A to B. Then there must have been a function somehow in between the two, a bijection. I don't have to find one function that's both injective and surjective. I don't have to actually find a bijection. If I can find one function that's injective and another function that's surjective, a bijection of some form must exist, even if I haven't explicitly constructed it. Proof. The proof isn't actually that long, I'm going to be honest, but I do consider it to be somewhat beyond the scope of this kind of introductory course. If this was a course devoted solely to set theory, we could probably go through it, but we're going to omit it. The utility of this, however, is that it allows us to sync up cardinality with an intuitive notion of inequalities when it comes to size. So we can say, if there is an injective function from A to B, then A is smaller than B. I was able to match up elements of A with elements of B without having to duplicate what I'm matching up to. So there are somehow fewer things in A than there are in B. So we can write that in the following way. The cardinality of A is less than or equal to the cardinality of B. And if there's a surjective function, I can stick elements of A onto elements of B and actually use everything up. So somehow there were like more elements here than there were over here. So I can write that as the cardinality of A is bigger than or equal to the cardinality of B. And this is all perfectly well and good and consistent because the Schroder-Bernstein theorem says, if there's an injection from A to B and a surjection from A to B, then there is a bijection from A to B, which means this inequality notation is consistent with how we're used to using inequalities. So the Schroder-Bernstein theorem allows us to write cardinalities in terms of inequalities like this. I can talk about one set having cardinality less than or equal to another, and I can talk about one set having cardinality bigger than or equal to another, and there's a sensible way of interpreting that about injections or surjections existing between sets. This does, however, lead to a discussion of what are infinite sets. So intuitively, we think maybe we might understand what the word infinite means, but here's a definition. A set is called infinite if there is a proper subset, namely a subset which isn't just the entire thing, but does have the same cardinality. So I can somehow remove elements from the set to make a proper subset that can still be put into a bijection with the original. So there is some subset which is not the same thing as the original, but has the same cardinality. There is a bijection between the set A and a subset of itself, which isn't everything. So it might seem surprising at first that you can actually ever find an example of a set that can be put into a bijective correspondence of everything with some stuff removed. But we've already actually seen this, okay? The natural numbers are an infinite set. Now, here's a subset, 1, 2, 3, and so forth. That's definitely a subset of the natural numbers. But 0 is a natural number, and I didn't put it into the set A, so I have a subset of the natural numbers, which is not all of them. Now, the function given by f of n equals n plus 1 is a bijection from all the natural numbers to all the natural numbers except 0. You can prove this function is injective in a fairly straightforward way. Now, it's not surjective onto all natural numbers, but it is surjective onto this set here. So it's a bijection. Therefore, I found a bijection between the natural numbers and a subset of the naturals that wasn't all of them. So the natural numbers are infinite. There are infinitely many natural numbers, surprising exactly nobody, but here's a nice proof of it. Now here's a theorem. Suppose I have an infinite set which is a subset of something else. Intuitively, A has to be bigger than B if B is a subset of it. So if B is a subset of A and B is infinite, then A must be infinite as well. The proof is actually not incredibly hard. But again, it's a little bit more detailed than we want to include in something that isn't a set completely devoted to set theory, a course completely devoted to set theory. There are some associated definitions that go along once we start talking about infinite sets. Specifically, a set is called countable if it has the same cardinality as some subset of the natural numbers. If it's countable and it's infinite, we say it's countably infinite. If it's not infinite, it's finite. So for example, z is countable. Okay, z, the integers, are countable because we in fact already showed through an explicit construction of a function that we could make a bijection between the naturals and the integers. So they have the same cardinality. So the integers are a set that have the same cardinality as a subset of the naturals, specifically all the naturals. So the integers are countable. And since we already know, by the way, the natural numbers are infinite and the natural numbers are a subset of the integers must also be infinite. So the integers are in fact countably infinite. In fact, the rational numbers are also countably infinite. So since the integers are a subset of the rationals, and the integers are infinite, we know that the rational numbers are infinite. And we can actually make an injective function going from the integers to the rationals, which is just identity. Plug in an integer, get out an integer, but interpret it as like 10 over 1 rather than just 10. So the cardinality of the rationals is at least as big as that of the integers. But it's possible to construct a surjection from the integers to the rationals as well. We're not going to give it here. I do encourage you to either try to look it up or come up with a way of doing it yourself. Plug in an integer, get out a rational number, and make it so that you can actually get out every possible rational number. That will tell you this inequality. Here we have an injection, so we get this inequality. Here we have a surjection, so we get this one. And then by the Schroder-Bernstein theorem, they have the same cardinality. And since we've already concluded that the integers have the same cardinality as the naturals, that means the rationals have the same cardinalities as the naturals, namely countably infinite. Well, we've talked a little bit about some infinite sets. Let's talk about some finite sets. Now, by definition, a set is called finite if it's not infinite, but that's not terribly helpful. Okay? It just means a set is finite if it can't be put into a bijective correspondence with any proper subset of itself. So here's a theorem. A set A is going to be finite if and only if its cardinality is the same as a subset of the natural numbers of the form 1 through n. Now what we understand, remember, 0 is a natural number. So if I say list out the natural numbers starting at 1 and ending at 0, I actually mean the empty set. There is no solution there. But list out the numbers from 1 to 1 would just be 1. From 1 to 2 would be 1, 2. From 1 to 5 would be 1, 2, 3, 4, 5, and so forth. Just understand that if I say list out numbers starting at 1 and ending at 0, we mean don't list out anything, you have the empty set. So if A is finite, it can be put into a bijective correspondence with a set of this form and vice versa. And in fact, there will be a unique choice of natural number in this case. So we can therefore say if this set is finite and it can be put into bijective correspondence with this set has n elements, so therefore A does as well. So a finite set can be said to have a specific number of elements according to which set of this form you can put it into bijective correspondence with. Now, as we've really gotten in the habit of in this section, we're not going to go through a proof. It's actually fairly tedious, in my opinion, to prove this, and it's extremely intuitive. Okay, a finite set has a finite collection of elements, and if there are a finite list of elements, then you list them out from the first one to the nth one, and you construct your bijection that way. You then just have to show that you can't put two different sets of this form into bijective correspondence with each other, which in my opinion is where it gets kind of unpleasant. It's fairly tedious, it's pretty intuitively clear, and it gives us a framework to say something like, let A be a set with 5 elements. Now we have gone through the background that says has 5 elements just means can be bijectively listed out as the first one, second one, third one, fourth one, and fifth one. Okay. And we can also just sort of say, look at this set, A, B, C, D. It's clearly finite, it has 4 elements, and now we've just formally justified that notion, but we're really not going to go through all the proofs. Okay. The good news is when we assume something should be true, and it actually is, that's a nice little congruence of events. Okay, we're going to close this out with a definition of what are called uncountable sets. Okay, because intuition can only get you so far. The real numbers are not countable. Remember, a countable set can be put into bijective correspondence with the natural numbers. Okay, the proof relies on some notions we haven't defined, so we are going to omit it. It's not terribly complicated. Okay, if you just search either YouTube or Google for something called Cantor's diagonalization argument, you'll quickly find many, many pages that give you this proof. It's not the hardest thing in the world, but it relies on some formal definitions that we haven't introduced, and I don't want to bother introducing just to do this proof. Okay, but if a set is uncountable, okay, it's not countable, we also call it uncountably infinite. Now this immediately implies that the cardinality of the real numbers is definitely bigger than that of the naturals. Because the naturals are a subset of the reals, then the cardinality of n is less than or equal to the cardinality of r, and this theorem says they're not equal. R is not the same cardinality as the naturals, so it must be actually bigger. In other words, the natural numbers are an infinite set and the real numbers are an infinite set, but in a very specific and concrete, showable way, the real numbers are an even bigger set than the naturals. In fact, Cantor showed that any set you have, you can always make a set with larger cardinality. Now, this sort of implies the existence of different sizes of infinity. Yeah, the natural numbers are infinite, but the real numbers are bigger than that. And, as Cantor pointed out, there's always a set with larger cardinality. So there can't even be a set whose cardinality is the largest of all cardinalities, because then there would be a bigger one by Cantor's argument. This was seen as an affront to intuition, and even by a good collection of people an affront to organized religion when this was developed, because it sort of said there's no such thing as the biggest of all infinities. And it says there are different sizes of infinity, and a lot of people do have trouble with this intuitively. Infinity is somehow supposed to represent the biggest thing, so how can there be bigger than infinity? Well, there are. Deal with it. Okay, it's not really a controversial thing anymore. Once you get through this formal definition, we're not really making any theological claims here. We're just saying, according to how we have defined cardinality, there are sets of different cardinalities, and there are sets with cardinality bigger than that of the natural numbers.